Hello everyone, welcome back to RC Circuits. This is lecture number 6. In today's lecture, we are going to discuss this problem which was not discussed in previous lecture, and we will quickly jump onto some other interesting topic. So the circuit is given and the 100 volt is applied for t greater than 0. So we have input voltage which is 100 volt for t greater than 0. So let's say at t is equal to 0 plus, then the circuit looks like this. The inductor does not allow the sudden change of current, so this will be open circuited and we have one dependent voltage source. This is how it looks like, and the voltage across the inductor for t is equal to 0 plus is, this is 100 and 10 ohms, 20 ohms, 20 ix. So ix is this. So this is VL of 0 plus. If you write nodal analysis at this node, then VL of 0 plus minus 100 by 10, which is nothing but ix. So this is ix current, which is minus ix. So VL of 0 plus minus 100 by 100 is this current, right? Because I have written this voltage minus this voltage. So but ix is flowing in this direction, so I have written minus ix. So this is one equation, and one more is the same ix is flowing here. So this node voltage is VL of 0 plus. So VL of 0 plus minus this node voltage is 20 ix by 20 is equal to ix. So I have just written this node voltage minus this node voltage by this resistor, which is 20, which is equal to this current, which is ix. So we have two equations and two unknowns, and we have to find VL of 0 plus. So if you find that VL of 0 plus minus 100 is equal to minus 10 ix, VL of 0 plus minus 20 ix is equal to 20 ix. So VL of 0 plus is equal to 40 ix. So if you multiply this equation 1 with 4, this is 1, this is 2, multiply 1 with 4, then 4 VL of 0 plus minus 400 is equal to minus 40 ix. Now minus 40 ix is minus VL of 0 plus. Is equal to minus VL of 0 plus. So if you solve this, 5VL is equal to 400. So VL of 0 plus is 400 by 5, which is 80 volt. So I got 80 volt. This is just to know, so the initial voltage across the inductor is 80 volt. So the voltage across the inductor is positive. Then the inductor starts charging, so it will build up its current. So that implies inductor starts charging, which implies current is built up. For t tends to infinity, the inductor will be short circuited. Then why inductor is short circuited? Because it is completely charged up. It means the current flowing through the inductor is constant at steady state, which means between the two terminals of inductor it acts as a short circuit. So this is short circuited because V is equal to L into di by dt, right? So if I is constant, then you will get VL as 0, and you have this. So like whatever, this part of the circuit is invalid, this right side, because all the short circuited current will flow, all the current will flow through this short circuit path. It does not flow through this branch. So this is 0 amps. So you will get all the current flowing through here, and you have 10 ohms. So IL of infinity is 100 by 10, which is 10 amps. So if you draw the waveform, then IL of t with respect to time, it will start at 0. Since we have positive voltage of 80 volt at t is equal to 0 plus, it will start charging up and it will charge to 10 amps finally. So this is 10 amps at steady state. It will charge in 5 time constants. So IL of t is 10 times 1 minus e power minus t by tau u of t. So this is the expression of the current flowing through the inductor. Now if you want to find the time constant, then for t greater than 0, you have to find the R equivalent across the inductor terminals. So let's quickly find that. R equivalent for t greater than 0, which is, you have to kill the independent sources. So you have to short circuit this voltage source, then this will be short circuited, and you have between these two terminals from left side, for left side you have 10 ohms, and if you check for right side, then there is one dependent voltage source. It is depending on the current flowing through 10 ohms branch, right? So this is 10 ohms Ix. You have to find R equivalent between these two terminals, and you have 20 ohms and 20 Ix. Yeah. Now if you want to find R equivalent between these two terminals, so the shortcut is, you have to apply test voltage or test current and find the current or voltage. So the simple way is to apply a test current of 1 amp and find the voltage across the current source, which is Vt. So since it is 1 amp and Ix is coming through here, 1 plus Ix current will flow here, and this node voltage is Vt. So since it is Vt, Ix is minus Vt by 10. So Vt is minus 10 Ix. This is one equation, and Vt minus 20 Ix by 20 is equal to 1 plus Ix. So I am just writing this current. 1 plus Ix is equal to this node voltage minus this node voltage, which is 20 Ix divided by 20. So Vt minus 20 Ix by 20 is equal to 1 plus Ix. So Vt minus 20 Ix is equal to 20 plus 20 Ix. So Vt is equal to 20 plus 40 Ix. So Vt is equal to 20 plus 40 times Ix is minus Vt by 10. So this is minus 4 Vt. So 5 Vt is equal to 20, Vt is equal to 4, which implies R equivalent is this voltage by this current, right? Between these two terminals, R equivalent is this voltage by this current. This current is 1 amp. So directly you will get R equivalent as 4 ohms. If R equivalent is 4 ohms, then tau is equal to L equivalent by R equivalent. L is 1, R is 4. So 1 by 4 seconds. So this will reach to steady state in 1.25 seconds. So this is about this circuit. This is a first order RL circuit. Now we will jump on to other topic, which is what is the capacitor behavior for constant current source. So we are pumping a constant current source of 1 amp through a capacitor of 2 farad, which has initial voltage of 0, and you have to find the output voltage across the capacitor. So for a capacitor, IC is equal to C dV by dt. So if you pump a constant current, let's say I0, then which is dVc is I0 by C dt. That implies if you integrate both sides, then you will get Vc is integral I0 by C dt. Since I0 is constant, because we are pumping a constant current source and C is constant. So if you take this term out, you will get integral dt, which is nothing but t. So Vc of t is I0 by C times t. Which means the capacitor current, if the capacitor current is constant, then the capacitor starts charging up linearly. So in all the previous questions, we have seen the capacitor charging exponentially, because we are not pumping any constant current source through the capacitor. The capacitor current depends on the input source, that is that we have applied, but here we are directly pumping some constant current through a capacitor. So then in that case, this will start charging linearly. So you will get Vc of t or V0 of t with respect to time, this kind of graph. Let's say we are applying this at t greater than 0. So this is 1 u of t, this current source. So from 0, the voltage starts charging up linearly, and this is nothing but this equation, right? Vc of t is I0 by C t. So here the slope is I naught by C. So if you go reverse also, the slope is constant, right? So because it is linear equation, if the slope is constant, then dv by dt is constant. If dv by dt is constant, C dv by dt is also constant, which means the current through the capacitor is constant. So if you apply reverse, then if you pump a constant current source, then the capacitor starts charging linearly. That is the conclusion. So this is how it looks like. I naught is here 1 and C is 2. So the slope is 1 by 2. So this is V naught, and here we have initial voltage of 2 volts. So initial voltage is 2 volts, and since we are pumping constant current, then the voltage will start charging up linearly, and the slope is I by C, which is 1 by 2. So if you write the equation here, so the initial voltage is 2 and I naught by C times T. So at T is equal to 0, we have V naught of T is equal to 2. That is what we are getting. And at T is equal to 1, it depends on the slope, m into x. So 1 by 2 into x plus the initial voltage, which is 2. So at T is equal to 1, this will charge to 2.5 volt. If this is 1, then this will charge to 2.5 volt. So for this one, the initial voltage is 2, but we are pumping, so assume all the current source are for t greater than 0, just for assumption. So V naught of t, since we are pumping the current in this direction, the voltage will build up across the capacitor in this direction. So this is positive and this is negative. That is what is asked also. V naught is we have given in this polarity. So but we have initial voltage across the capacitor in this direction. So first you have to make that to 0, and then it will start charging up in positive direction. So initial voltage is minus 2 volt. If you take in this direction, then this starts charging up with the slope of 1 by 2. So V naught of t is initial voltage is minus 2 volt, then 1 by C, I naught by C, which is 1 by 2 t. So here the slope is positive. So we got this expression. And for this circuit, if you draw V naught of t, the same here, the current is flowing in this direction, which is 1 amp for t greater than 0. But he is asked to find the voltage in this direction, which is opposite to the capacitor charging. So we have initial, if you draw Vc of t, then it looks like this. The initial voltage is 2 volt, right? And it is charging in this direction. I am considering Vc of t in this direction. Let's say Vc of t is this one. So we have initial voltage of 2 volt and this starts charging in this direction, that is Vc of t if I consider in this direction. Then but he is asked V naught, right? So V naught is in opposite direction of Vc of t. So initially V naught is minus 2 volt because 2 volt is in this direction. So this is minus 2 volt, and the capacitor starts charging in this direction, which means V0 is in reverse direction. So if the slope of Vc of t is positive, then the slope of V0 of t is negative. To get the negative slope, then it should look like this. So this has a slope of minus I by C, which is 1 by 2. I by C is the capacitor voltage slope, right? The voltage across the capacitor has a slope of I0 by C if we pump constant current through the capacitor. So that's why I am saying for every time the slope is I by C, so which is minus 1 by 2. So you understand this one, right? So V0 of t is initially minus 2. Now we have negative slope of minus 1 by 2 and it is linear. So minus 2 minus 1 by 2 t. This is the equation of V0 of t. So what is the conclusion? Conclusion is, if we pump a constant current through a capacitor of I0, constant current of I0, let's say through a capacitor of C, then the capacitor voltage starts charging linearly with a slope of I0 by C. So that is a conclusion from above analysis. And if you find the time constant of the circuit, so this is also a first order circuit, right? No, but we will discuss that later. But just a second. Yeah. So to find the time constant of the circuit, then you have to open circuit the current source, right? So if you open circuit the current source, then you have a capacitor and a open circuit. Open circuit in the sense R equivalent is infinity. So C equivalent times R equivalent is infinity, which is nothing but the time constant is infinity. I am saying the time constant is very high. What does it mean? It means the circuit is taking infinite time to reach to steady state. It means it is not reaching to steady state indirectly. So if you look at here, is V0 is reaching to steady state at some point? No, right? Because the time constant of the circuit is infinite. So that is what I am trying to say here. And yeah, this is about if you pump constant current source through a capacitor. Now, what if you give infinite current or impulse current through a capacitor? So first of all, what is this impulse current mean and what is this infinite current meaning? Infinite current is not practical, because how can you pump an infinite current from any source meter? That is not possible, right? Which does not exist. So first of all, this is not practical. So assume in theory we have infinite current, so which is represented by I of t is equal to infinity. So it means you are pumping very high current through a capacitor. That is what infinite current meaning. And what is this impulse current? This is practical, which means we are pumping a finite amount of current within very short duration, and that finite implies very high magnitude. So I am saying, so infinite is, suppose at t is equal to 0, at t is equal to 0 you are giving infinite current. That is what infinite means, but that does not exist practically. So we come to concept of impulse current, which means we are giving within very small duration of time, we are giving very huge current, and immediately we are making it to 0. It means it is a very high rectangular pulse. So very high rectangular pulse within no time. So it means for t tends to 0, the magnitude of current is very high. So this is what the impulse current means. So for impulse current, area is finite. So what does the area mean? Area is the integration of it, right? So what is integration of it? We know I is equal to dq by dt. So what is q? Integration of I dt. So which is nothing but charge. So if the area is finite, which implies the charge across the capacitor is finite. So finite charge for a capacitor. So we represent the impulse current like this. So let's say this is I of t. We represent with an arrow symbol. So this is what the impulse current means. And if you write the magnitude, then this represent the area under the curve, which means the charge. So in mathematical expression, we write impulse current as, if the magnitude is I naught, then we have to write I naught del of t. Del of t is the impulse function. So yeah, if you integrate I of t, then integration of del of t is 1. So and I naught is constant, so you will get the magnitude. So this magnitude is charge. So this is about impulse current. So if you pump an impulse current through a capacitor, what will happen to capacitor? How can we add page here? So if you pump the impulse current through a capacitor, so this is I naught del of t. Then what will happen? So forget about the equation, just what is the relation between capacitor voltage and current? I is equal to C dV by dt, right? So if I is equal to C dV by dt, then if the current is very huge, if the current is impulse, which means it tends to infinity at within no time, right? So it means the dV by dt is very high, which means there is sudden change of voltage within no time. That is what it indicates, right? So which means the capacitor behavior is not acting like we have seen in previous classes, right? Actually the capacitor does not allow the sudden change of voltage, but here, since the impulse current is flowing through the capacitor, there is a capacitor voltage abnormality. It means there is a sudden change in the voltage across the capacitor within very short duration, within no time actually. So that is what it means. So I is equal to C dV by dt. The impulse current is I naught into del of t C dVc by dt. So dVc by dt is I naught del of t dt by C. So Vc of t is integration of I naught by C del of t dt. So U of t differentiation is del of t. Why? Because U of t is till t is equal to 0, it is 0. At t is equal to 0, there is sudden change. So if you differentiate this equation, this is constant, this is constant. So if you differentiate, you will get 0, right? From here to for t less than 0, for t greater than 0. But at t is equal to 0, there is a sudden change, right? So within no time, it is going from 0 to 1, which means you will get one impulse at t is equal to 0. So that's why this is U of t, this is del of t. So if you differentiate U of t, you will get del of t, which means if you integrate del of t, you will get U of t. So I naught is constant, which is the finite area, right? So Vc of t is I naught by C U of t. So if you draw Vc of t, then at t is equal to 0, it is going to I naught by C. So there is a sudden change in the capacitor voltage at t is equal to 0. So that's why because we are applying an impulse current. So conclusion is impulse current through a capacitor implies sudden change of voltage across the capacitor. So this is one way. So you have given a capacitor. If you want to do a sudden change in the capacitor voltage to disturb the actual behavior of capacitor, then there are two ways. Either you want to pump a impulse current, a huge current through a capacitor, then there will be a sudden change in the capacitor voltage. One more way is without any resistor, directly you can apply a voltage, right? Directly a voltage source to a capacitor. So let's say the initial voltage is 0 and you have directly applied, let's say, 5 volt. So at t is equal to 0, you have applied 5 volt directly to a capacitor. So definitely this 5 volt is in parallel to the capacitor terminals, right? So then you will get till t is equal to 0, the voltage is 0. So immediately, since we have applied directly to the parallel of the capacitor, then it will be 5 volt directly. So how will the capacitor voltage change suddenly here? Because by taking the very infinite, very high current through it. So this sudden change of voltage by taking impulse current through it. So that's why impulse current is very high current, right? So for any practical capacitor, there should be a voltage limiter, current limit. So that's why practically you should not apply directly a voltage source across the capacitor, otherwise it may damage, because for very short duration there will be very high current flowing through the capacitor. That's why you have to always charge the capacitor through a resistor in series. So that is how you have to do. And yeah, that's about the impulse current through the capacitor. Okay, so here we have applied 5 volt at t is equal to 0, right? So the voltage source is at t is equal to 0 directly 5 volt. So there is a sudden change at t is equal to 0, right? Which means it is very high frequency at that time instant only, not at steady state. So that is what it meant. So instant DC source change means the capacitor thinks a very high frequency is applied at t is equal to 0, which means the frequency tends to infinite, because within no time we have applied a 5 volt, right? So that means a very high frequency, omega tends to infinity at t is equal to 0. So that's why we have to okay, so the capacitor, the impedance of the capacitor is 1 by j omega c. So if you put omega tends to infinity, then you will get a 0. The 0 impedance means it is a pure short circuit. So that's why at t is equal to 0 we replace the capacitor with a short circuit. That is one way to explain. So because at that instant we can assume omega tends to infinity. So sudden change in DC source, which means omega tends to infinity, which implies the capacitor is short circuit at that instant. So, or we can say it is very low impedance. And for inductor, it is opposite. Since the impedance is j omega L, if you put omega tends to infinity, so at t is equal to 0, it acts as open circuit, which is nothing but very high impedance. And for sudden change in DC source, this is only, let's say at t is equal to 0, we have sudden change. So this is at t is equal to 0 plus all this behavior is happening. So the capacitor is short circuited, so we simply represent as resistor. and it is very low impedance. And since it is short circuited, we can represent directly a capacitor, and this is very low impedance because omega is tends to infinity. And for this one, this will be open circuited, right? So like if there are two impedances and this is very high, let's say this is Z1 and Z2. If Z2 is very high, Z1 plus Z2 is approximated by Z2, right? So which implies we approximate this with inductor, and which is in series with, this impedance is very high. So omega tends to infinity, high impedance. And here, if this is high impedance, then if two impedances are in parallel and one is high and one is low, then it is approximated by the very low impedance, right? Suppose you have 1 ohm and you have impedance of 10,000 ohm, which is nothing but approximately you will get 0.9999, right? So which is nothing but the lower impedance. So if omega tends to infinity, this impedance tends to open circuit and you will get only a resistor. So that is how the circuit behaves at that instant if we have a resistor and capacitor or resistor and inductor combinations. But when it comes to steady state, which means there is nothing is happening in the source, which means the frequency is 0. So omega tends to 0. So if omega tends to 0, then 1 by j omega c is tends to infinity, which means the capacitor will be open circuited, and j omega l tends to 0, the inductor is short circuited. And similarly, if the capacitor is open circuited, this is at steady state. So for steady states only, so this is lower impedance and this is not lower impedance, but compared to this is very high impedance. It's almost open circuited. So we represent it with capacitor, and which is high impedance, omega tends to 0, and this is very high impedance and this is open circuited, so you have only a resistor. And this will be short circuited for omega tends to 0 at steady state, so you will get only resistor. And if this is short circuited, then all the current will flow through here and we can ignore this one. So it looks like this circuit has only inductor and there is no across branch, so we can ignore this R, so it will be only inductor. That is how this behave for steady states. And yeah, we can know about a simple Laplace transforms of some functions. So for impulse function, the Laplace transform is constant. So here the magnitude is 1, so you will get 1. For a unit step function, the Laplace transform is 1 by s. And for ramp function, ramp is nothing but linear, that we have seen if we pump constant current through a capacitor, right? You will get ramp function. So for ramp function, the Laplace transform is 1 by s square. So this Laplace transform we may use in our upcoming problems. So that's why I am just discussing briefly about this Laplace transforms of some functions. So for a capacitor, impedance we represent in Laplace transform. So we know the capacitor impedance is 1 by j omega c, right? So always S is equal to j omega. So remember this one, S is equal to j omega. So if you substitute this one, you will get 1 by sc. So this is 1 by sc. And for inductor impedance, you will get SL because it is j omega L. So if you have some initial voltage across the capacitor, then okay, this we represent in time domain as a constant voltage source in series with a capacitor, right? So if you transform into Laplace transform, this branch looks like this, which is V naught by S, because for a constant, for u of t it is 1 by S, right? So for V naught it is V naught by S, and the capacitor 1 by Cs. So if some I naught of t current flowing through that capacitor, let's say IC of t, and this is V naught, then this complete voltage across this branch is V naught, right? So this is V naught of t, which is nothing but this is V naught of S, and this current is I naught of S. You can also represent like, so if a voltage source in series with a impedance, it can be represented by a current source in parallel with the same impedance, and the current source value is this voltage divided by this impedance value. So this is the voltage source to current source transformation technique. So this is nothing but V naught by S by 1 by Cs. So you will get C into V naught. So this is CV naught in parallel with the same impedance. So this is 1 by Cs. So these two terminals have represented as these two terminals. So this total current is now I naught of S, and this voltage is V naught of S. So this is about the capacitor. Similarly, if you have a constant current, an initial current of I naught, then in time domain you represent with an inductor in parallel with the initial current, right? So if you remember, at t is equal to 0 plus, we represent it as a constant current source, and the current source value is the initial current. So if this is I naught, then this is I naught. So but this is for t greater than 0. At t is equal to 0 plus, this inductor will be open circuited, right? So you will get a constant, only a constant current. So this is inductor. So if you transform this into Laplace transform, then the impedance is SL, and constant value is I naught by S. So this is V naught of S, and this total current is IL of S, which is nothing but, so current source in parallel with an impedance, which is nothing but a voltage source in series with the same impedance. So the same impedance, which is SL, and a voltage source. The voltage source polarity should be like this because the current flowing is in this direction, right? So the polarity of voltage should be such that it should be plus and minus, and it should give the current in this direction. So that's why, yeah. And the voltage source value is the current times the impedance, which is nothing but I naught by S into SL. So L into I naught. So L I naught. And this total voltage is V naught of S. This current is IL of S. This is how you represent the inductor if you have some initial current through inductor, and in Laplace transform you have to represent like this. So, and I think we have already discussed this problem. What if you pump a constant current source through a capacitor? So you will get a sudden change in the voltage across a capacitor. So that is this one. Yeah, this problem. So I think it's done for today, and we can discuss. We have discussed more about theory today. What if a constant current through a capacitor, and similarly, if we apply a constant voltage across the inductor, you will get the current through the inductor linearly. And we have also seen what if you pump a impulse current through a capacitor, there will be sudden change of voltage. So depends on this theory. We will discuss more problems in coming lectures. So if you have any doubts, you can comment down. We will try to answer. And if you like this video, please share to your friends. Yeah, thank you.